4.5 and 4.6 focus on this idea of the absolute maxima and minima. So it's going to be similar to finding local maxes and mins. In a sense, there's obviously some carryover to that, critical numbers, that sort of thing. But the point of finding absolute max and minima here in 4.5 is not so that we can graph. It's because we're going to get some cool applications in 4.6 called optimization. So this is going to set us up. We're going to see the mathematics, and then we're going to put it into practice in some word problems, some applications in 4.6, kind of like when we first learned implicit differentiation. We then immediately used it in related rates, like that was the carryover to the application. Okay, anyway, what's this all about? The absolute max and minima. Well, let's go ahead and define the absolute max and the absolute min, and they're probably what you're thinking they are. We define the absolute max as the highest y value of a function on an interval. So notice that it's not the full point. We don't care about the ordered pair. Like we do a local max or a local min, we like the ordered pair. An absolute max, we just care about the y value, and it will always be on some interval. Even though the domain of the function might be all real numbers, we're going to restrict that domain, and we're going to say start at A, end at B. So we're going to see that in the examples we do. Similarly, the absolute min, well, that's the lowest y value on your interval. Let me give you a drawing just so we can all see what's going on here. So I drew this simple function, not a whole lot going on here. Almost looks like a piece of a parabola, right? But it's only the part that begins at 5 there and travels up through the 0.17 and then drops down to the 0.42. So here you might say your interval is from 0 to 4. Just that restricted part, we might say. Well, what is the absolute max and what is the absolute min? And well, we can just see those things. So the absolute max is the biggest y value, the highest y value being 7. The absolute min is the lowest y value, 2. Now, one thing you notice here, that absolute max in this example occurs at a critical number, right? The slope of the tangent line right there is 0. That would be a critical at 1, you might say. Where the min does not occur at a critical number, that occurs at what we'd call an endpoint. So the endpoints are 0 and 4. So that would not have, 4 would not have come out in your critical numbers. But we can notice, well, but it was an endpoint. So endpoints, might possibly be a local min or even a local max. Okay. Let's get to the steps in finding an absolute max or min. So I've laid out a 3-step procedure here. This chapter is all about steps. Follow the steps. Remember what the steps are, right? That's important. Okay, so to find an absolute max or min of a function f of x on the interval from a to b, step number 1, we're going to find all the critical numbers in AB. Yeah, okay, let's go with that. Then, once we find the critical numbers, we're going to find the y values of those critical numbers. And we're going to find the y values of the endpoints at x equals a and x equals b. So once we have the y values of the criticals and the y values of our endpoints, that will give us all of the candidates, if you will. Those are the possible absolute max and absolute mins. Once we get those y values, those are like the important y values, you might say. Once you have that list of y values, well, then it's real simple. You just pick the biggest one and the smallest one. So out of all your y values, the highest one of them is your absolute max. And out of all your y values, the lowest is your absolute min. We know that has to be true because the criticals are the places where it might change from increasing to decreasing. And so if there hasn't been a change, then we know that, it can't be a max or something. So the maxes have to occur at the criticals or the absolutes. The absolutes is what I'm going to say. The absolutes have to occur at the criticals, or the absolutes have to occur at an endpoint like we saw in that drawing a moment ago. Okay, let's get to it. Find the absolute extrema. Just one example here before we talk about another idea. The absolute extrema. Okay, so we've got f of x equals x squared minus 6x plus 7. And we're going to restrict the domain to be 0 to 10. So let's follow our steps. Step number 1 was find the critical numbers. So to find the critical numbers, of course, we need the derivative. Not a big challenge here. 2x minus 6. And then, of course, to continue to find the criticals, we need to find where that derivative equals 0 and where that derivative does not exist. And so since we've done this quite a few times now, I'm just going to show you what I got here. So when the derivative equals 0, we wind up with x equals 3. For that derivative not existing, well, you're never dividing by an x, so that's a none. We get the one critical number, x equals 3. Okay. Step number 1, done. Step number 2 was find the y values of the critical and find the y values of our endpoints, 0 and 10. So I'm just going to go for it, and actually I'm going to end up showing you the whole rest of the problem when I do this. No big deal. So we take the y value of our critical, we take the y value at both of our endpoints. That means we need to plug it back into the original function. So when I plug 3 back into the original, x squared minus 6x plus 7, plugging in 3, I got negative 2. Okay. When I put 0 into the original, I got 7. When I put 10 into the original, I got 47. So these are the 3 important y values, or like the critical y values maybe. So I'm going to pick the biggest one, that's my absolute max, 47. And I'm going to pick the smallest one, that's my absolute min, negative 2. Done. We got it. Now when you're doing your homework, I highly recommend, when you finish a problem, or if you run into trouble, graph that in Desmos. And then you'll confirm your answer. So it turns out this one, if you were to graph, so at 0, it starts off at 7, okay? Then it drops, and out here, didn't really give myself very good. So there's 0. Then it drops to a min, and then it's going to shoot up, and by the time you get to 10, it's way up there. So here it's way up at 47, and there's negative 2. It does that sort of a thing. This is at 3, right? So there's your absolute min. There's your absolute max, happens to be the endpoint on the max. And 7's just kind of halfway in the middle, so we don't consider it. It's not a local, it's not an absolute max or min, obviously. Okay. What else are we going to talk about here? Sometimes you have to employ the second derivative test, and it's not clear why we would need this just yet. Hang on, follow me with what the test is, and then we'll do an example and we'll see why we need it. Okay, so you might remember the first derivative test back in 4.1. Now finally we get the second derivative test, and as you might guess, it's going to involve the second derivative. Although it's still testing for extrema, maxes and mins. Okay, how are second derivatives, how can they help us find maxes and mins? Well, let's see. Let's say x equals c is a critical number, and specifically a critical number that made the first derivative equal to 0. Okay. Obviously, other critical numbers might cause your derivative to not exist, but we're not considering those, only the ones that make your derivative 0. Okay. So here's what we're going to do. We're going to take that c and we're going to plug it into the second derivative. Okay, so let me go ahead and read this first part. If the second derivative at c is positive, then there is a local blank at c. There's a reason I left that blank. We're going to think about it. If the second derivative at c is negative, less than 0, there is a local blank. Obviously, well, it'd be the opposite of whatever the other one was. Now, if we were in class, I would say, hey, how do we fill in this blank? Maybe the first one. If our second derivative is positive, is it a local max or is it a local min? And kind of see what people thought, and or if maybe there was some people who thought they knew it right away or something. Turns out this is the opposite of what you might immediately expect, or what most people immediately expect. It's the opposite of that. What's going on here? So if the second derivative is positive, second derivative is about concavity, right? If the second derivative is positive, that means it's concave up. It's doing this, right? Well, does a curve like that have a local max or a local min? It has a minimum there at the bottom. You might think, well, how do we know our point is at the bottom? Because we already said the first derivative is 0. So if the first derivative is 0, that means we have a horizontal tangent line. So if these things combine, horizontal tangent line and concave up, it had to be a local min, right? Combine those two aspects. It's got to be a min. And in the second one, hey, second derivative is negative. That means you're concave down. And we know the first derivative is 0. That means you've got a horizontal tangent line. Well, if you combine those two, that's a local max. So it ends up being the opposite of what you think. Normally we think positive, and negative, kind of, they should go the other way. But here, concave up means it's got a min. Concave down means it's got a max. And I drew these things again here. Min, max. That'll be good. So when you apply the second derivative test, I'm going to do this in the example, and I encourage you to. When you get that answer, think concavity, and even write, oh, that means concave up if I got this one or whatever. And then that'll help you visualize whichever case it is. Just a quick example before we get into the big example, talking about absolute maxes and mins. And let me go ahead and just get that off the screen so it doesn't confuse us. Let's try, just really quick, applying the second derivative test to f of x equals x to the third minus 3x. So if we do that, what we're going to do is take the first derivative, and remember, we need to know the critical numbers that cause the first derivative to equal 0. So we take our derivative, we set it equal to 0, and I'm not showing all the steps because, again, we've done it so many times, but also this is a fairly straightforward one. This would lead to two answers, positive and negative 1. That would cause the first derivative to equal 0. Okay, so we got these two critical numbers. So what are we going to do? To determine if they are maxes or mins, we're going to look at the second derivative. So, my first derivative is 3x squared minus 3. My second derivative, well, that had to be 6x. And I'll just show you here everything. So what we're going to do, we're going to say, let's take the positive 1, put it into the second derivative. Okay, when I put positive 1 into the second derivative, I get 6. Now it's not the 6 I care about, it's the fact that it's positive. So I know it's concave up. And combine that with the fact that it causes the first derivative to be 0, I know I've got a min, a local min, technically. Although we're going to be talking about absolutes, but you technically as a local min. At the other critical number, -1, well, putting in that into my second derivative gives me -6. Again, it's not the 6 I care about, it's just the fact that it's negative. So I know I'm concave down there. Well, if you're concave down and your first derivative is 0, there's got to be a local max happening. Okay, I'm going to stop this video here. We're going to get into the examples using the second derivative test in the next one.